right, well, welcome to calculus. So section 1.1 is a review of a lot of stuff you've done before. Nothing is really very new, so we'll try not to go through it too quickly, but in some sense we will go through it quickly just because it's a lot of review. So we're looking at functions and models in this section. So first of all, let's just remind ourselves what a function is. So a function, we usually denote f. Well, you know, there's other things that we can call functions, g, h, whatever, but you know, the most common is f. So function f is a rule that assigns to each element x in a set D exactly one element called f of x in a set E. Okay, so we've got these two sets, D and E. Okay, and so x, that's the thing that we put into our function. That's our input. So this is going to be our input. And our input comes from this set D. So input comes from D. So D is the domain. That's the set of all possible inputs. So the domain is the set of all possible inputs. And in this case, it's D. Okay, so that's our first one. Once we get our input value, and then the function f assigns, okay, there's some kind of rule that assigns an exactly one element, and it's called f of x. Okay, so this whole thing, f of x, this is our output. Okay, and the output comes from a set E. Okay, and that's the range. So the range is the set of all possible outputs. Okay, and in this case, that's E in our definition. Okay. All right, so this is the range. This is the domain. I'll put outputs here. All right, so we're familiar with that. And then the next thing that we have to look at is the terms independent variable and dependent variable. So the independent variable is the thing that we're allowed to freely change. Okay, and that's the input value. Okay. So we can change this. Okay, and then the dependent variable, okay, this is the output. Okay, and this responds to or depends on the input value. And of course, that input value is the independent variable. So in terms of our definition up here, x, okay, this element x, that's our independent variable. And f of x, this value, the output, that's our dependent variable. And often we'll call that y instead of f of x. Okay, because this, you might be looking at this, go, that's not a variable. Well, it's okay, it's equivalent to a variable. Sometimes we'll call it y instead though, so it will be just a single variable. All right, so that's our terminology that we've seen before. Hopefully nothing too new or shocking there, but it's a good review. Okay, so now that we know what a function is, there's several different ways that we've seen in the past that we can represent functions. So probably the most common way that we'll see functions is to represent them algebraically in some kind of an equation or some kind of an explicit formula, like this formula right here that gives us the area of a circle. Okay, so our function a, okay, that's the name of the function is a, and then in the parentheses we show what the dependent variable is r. That's the thing that changes. Okay, so the radius, and based on whatever the radius is, okay, this dependent variable or the function value will change when we give it a new radius value. Okay, and so this R is our independent variable. Okay, and then this whole value right here, that's the output. Okay, or the dependent value. So that's how we're used to seeing them. Of course, sometimes we see things that are set up in tables. Now, I know this is kind of hard for you to see. It's not important really what's in the table, more that we can represent a function with a table. This has a list of different years and populations from that particular year. Okay, and so in a table, okay, this value, and usually that all of these, this whole set here would be our domain. Okay, and then if we're talking about a variable, okay, that represents the year. So the year would be our independent variable. Okay, and then the output is the population. This is going to be the dependent. So the population depends on what year it is. So this is our dependent variable. Okay, if we took all those populations and put them together, that would be our range. Okay, so our function, we can take any value from the domain, and like if it's 1940, then we'll map a value from the range. In this case, it happens to be 2,300, and I guess this is in millions, times 10 to the 6th. Okay, so there's just this mapping between input values from the domain to output values from the range. All right, third way that can we represent functions is verbally. Okay, and this might happen if we can't really write an explicit formula for it, and maybe we can't list them in a table very easily either. For example, this one, associate the nth prime number with the number n. Okay, so we know there's no formula for finding the nth prime number. There's no pattern. Nobody's ever been able to find any kind of pattern or any kind of formula to generate prime numbers. Okay, so we can't have a formula, and we can't even really put them in a table. We don't even know what all the prime numbers are, and plus there's an infinite number of them, so trying to write a table wouldn't really work because there's an infinite number of them. So the only way to really describe this function is to just write it out verbally. So we know that the nth prime number, like the first prime number, is 3. So we would map 1 to the prime number 3. So our input is going to be this n value. Okay, this is our independent variable, or our input. And then the nth prime number, that will be our dependent variable, or the output. So if I put in the number 3, the third prime, what would the output be? Well, the third prime would be like 3, 5, 7. So the output would be 7. That would be our dependent value. Okay. And the fourth way that we can see a function being represented is visually by a graph. And so if you look at this, it's an example from your book. This is from a seismograph. We're looking at the acceleration of the Earth in centimeters per second squared over time during an earthquake. Okay, and so trying to put this kind of data into some kind of a algebraic function wouldn't really work. Even trying to list out in a table, I mean, you could maybe give some values discretely, but this is a continuous, okay, time lapse kind of thing. So even putting in a table doesn't work very well, and trying to describe that verbally is very difficult. Okay, but you know, you can record this kind of data in real time and the graph gives you all of the information. Okay, so once again, whenever you have a graph, the independent variable is always going to be on the horizontal axis. We think of that as the x-axis normally, but this is the t-axis in this particular function. But it will always be the independent variable here. and then the dependent variable will always be on this axis. Okay, the vertical axis. Okay, so time in seconds is the independent variable, and then the acceleration is the dependent. Okay. So most of the time, and especially in calculus, we're mostly going to be looking at the algebraic examples and formulas using function notation. Now, one thing I wanted to point out here is that there's a special thing called the difference quotient, and you probably remember having to do a bunch of problems like this in pre-algebra where you had to find, f of a plus h minus f of a over h. And the reason you had to do that so often is because this shows up lots and lots and lots and lots in calculus. We're going to do this over and over and over again, especially in the next chapter. So we need to get really, really comfortable with function notation and how to compute this kind of a difference quotient. But this is the formula for what they call a difference quotient. So if they say compute the difference quotient, that's what it means. Do f of a plus h minus f of a divided by h. Okay, so let's do a couple of examples. So we'll start out with this one. We've got f of x, and it's defined to be 3x squared minus 5x plus 4. So remember that we think of this as f of box equals 3 times box squared minus 5 box plus 4. Okay, and so if we want to do f of a plus h, we put a plus h into the box. So f of a plus h, okay, minus f of a over h. Alright, so f of a plus h, so put this in the box. So that's going to be 3 times a plus h squared minus 5 times a plus h plus 4. That takes care of f of a plus h. Okay, we took a plus h and put it in this box and put it in this box. Okay, now minus, and it's a really good idea to put parentheses because we need to subtract all of f of a. Okay, so we're going to take a and put it in the box here and here. So that'll be 3a squared minus 5a plus 4. And that whole thing will be divided by h. Okay, so we have to square this. That'll be 3 times a squared plus 2ah plus a squared. And I'll go ahead and distribute this one. Minus 5a minus 5h plus 4. Distribute this minus 3a squared plus 5a minus 4. Okay, let's go ahead and now distribute the 3. So we've got 3a squared plus 6ah plus 3h squared minus 5a minus 5h plus 4 minus 3a squared plus 5a minus 4, all of that over h. Okay, so we've got a plus 4 and a minus 4. Those cancel each other out. We've got a 3a squared minus 3a squared. Those cancel each other out. We've got a plus 5a and a minus 5a. Those cancel each other out. Okay, so let's see what we have left. So I'm gonna put this 3h squared first. So I've got 3h squared. Okay, so that takes care of this one. And then I'll do this plus 6ah, so that takes care of that one. And then minus 5h, that takes care of that one. All right, so that's our whole numerator over h. Okay, I'm kind of running out of room. I'm going to go this direction even though I like to go down. But all right, so we'll factor out an h in the numerator. That would be h times 3h plus 6a minus 5 all over h. Those h's can cancel out. So our final difference quotient would be 3h plus 6a minus 5. Okay. All right, let's try one more. Okay, so that one was a good one for us to practice, okay, because we had to square this thing and make sure that we put our parentheses in so that we distributed our minus. Okay, this one's going to be a good one to practice because we're going to have complex fractions. Okay, so once again we want to do, so notice this is f of box equals 1 over box plus 3. That's how you want to think of it. Okay, so when I do my f of a plus h, I'm going to take a plus h and put it in the box. Okay, so 1 over, I put a plus h in that box, plus 3. Okay, so that takes care of f of a plus h. And now minus f of a, so I'm going to take a and put it in the box. So I have 1 over a plus 3. Okay, so that gives me f of a plus h minus s of a, and that's all over h. Okay. All right, so that means we've got to find a common denominator so that we can combine these two fractions up here. Okay, so I'm going to have to multiply this one by a plus h plus 3 over a plus h plus 3. And I need to multiply this one by a plus 3 over a plus 3. And that'll give me a common denominator. All right, so I've got a plus 3 times 1, and then minus 1 times a plus h plus 3. Okay, all over the common denominator of a plus 3 times a plus h plus 3, and this whole thing divided by h. Okay, so if I want to get rid of this complex fraction, I can multiply everything by 1 over h over 1 over h. I'll cancel those out. Okay, so in my numerator up here, I've got a, and then it'll be minus a. Well, let me just write it out. So minus a minus h minus 3. Okay, and in our denominator we've got h times a plus 3 times a plus h plus 3. Okay, I have a plus 3 and a minus 3. I have a plus a and a minus a. So I just end up with minus h over h times a plus 3 times a plus h plus 3. The h's cancel out. And so my final answer is negative 1 over a plus 3 times a plus h plus 3. Okay. All right, so hopefully that's a good review of how to use our function notation, complex fractions, careful uses of parentheses, okay, all the things that you need to retain because they're going to keep on coming up over and over again in calculus. Okay, so if we have a function, there's a couple different ways that we can visualize it. Sometimes you'll see this thing called an arrow diagram, and these are kind of popular when we have these kind of discrete functions where I have a finite domain and a finite range, and there's some kind of mapping there. Okay, so it'll show you that this on the left is always the domain, and on the right is always the range. And then these little arrows in the arrow diagram show you how, okay, the number from the range gets assigned to the number of the domain. So if 5 is the input, then 6 is the output. If 7 is the input, 6 is the output. If 3 is the input, then 7 is the output. If 8 is the input, 9 is the output. So those little arrows just show you the relationship. Okay. So that's what the little arrow diagrams tell you. Okay, now one thing to note is that in a function, we must have a unique mapping okay, from a domain value to a range value. Okay, so sometimes students get confused about this and say, oh, this can't be a function because this 6 right here has 2 arrows coming into it. That's fine. The only issue is that if we have an input value, we have to unambiguously be able to tell what the output value is. And if I have the input of 5, I absolutely know the output is 6. If I have an input of 7, I absolutely unambiguously know that the output is 6. It's no problem. This is a function. Okay. Over here, where we have 2 arrows coming out of something in the domain, that's when we have an issue. Okay, because when I have an input of 2, what's the output? Well, I can't unambiguously tell you whether it's 3 or 4. It could be either. Okay, so this is not a function. Okay, because 2 does not map to unique value in the range. So 2 in the domain. Okay, so this is a relation, but not a function. Okay, and the way that you can tell in these mapping diagrams or these arrow diagrams is you have to look for 2 arrows coming out of a domain. That's when you'll know it's not a function. Okay, here where I've only got 1 path out of each domain value, then those are functions. The other way to visualize a function is with a graph, like these ones. Okay, and we know for a graph, the way to tell whether or not it's a function is by using the vertical line test. So the vertical line test says that if I have a vertical line and it only passes exactly once through my graph, then it will be, did I say exactly once? If I have a vertical line, any vertical line passes through my graph at exactly one spot, then it's a function. Okay, so notice, okay, that this passes the vertical line test. Okay, because it's a function. This one passes the vertical line test. It's a function. This one passes the vertical line test. It's a function. Okay, there is an asymptote in this one. Okay, but it never actually goes straight up and down. This approaches that line but never reaches it. So there isn't a vertical line that will actually pass through this part or this part of the function twice. Okay, so one thing to note in this book, domains and ranges and things are all given using interval notation. So if I were going to look at the domain and range of this one, I would just use set notation. I would go, oh, well, the domain is just the set of 5, 7, 3, and 8. And the range is just the set 6, 7, and 9. I would just use sets. Okay. But notice, if I try to list the domain and range of this function, it's impossible. There's an infinite number of inputs, and so I can't just list them all. Okay, so I have to be able to have some kind of notation that allows me to have an infinite number. Now, in the past, let me just, okay, would have said, okay, well, the domain of this is, well, let's see, so all legal values of x are from -5 up to 1, so we would have said, oh, that would be all real numbers such that x is between 5 and 1, and then x is also then greater than 2. And we would have written it that way. Okay, so that's fine. That's a fine way to write the domain, but that's not the way that your book does it. So our calculus book is going to use interval notation. So in interval notation, we use these brackets. Okay, so a square bracket will be for a filled circle. Okay, so it starts at -5, so we would have this square bracket to show that -5 is included in the interval. Okay, and then it goes all the way up to 1, which is also included, so you just put a comma. So the left bound up to the right bound, it goes up to 1. 1 is included, so I would put a closed bracket there. Okay, now there's nothing in this interval between 1 and 2, but then it goes again to 2. But 2 has an open circle, it's not included. I'm giving myself a little space here. I have a parenthesis there with 2 to show that 2 is not part of the interval. Okay, and then it goes all the way up to 5 and stops there. 5 is part of the interval because it's the closed-in circle, so that would be a square bracket. Okay, and then to show that I put these two things together, I put a union symbol in the middle. So that's a set symbol. It's this interval unioned with this interval. Okay, so the two of those things put together. So that's how I would specify the domain. Okay, if you think about how we used to write the range, we would say, oh, well, the range is all real numbers y, and then specify them. Well, the range of this one, the y values, well, it could be as small as -2, and then it still, it still gets those values in there. It can go all the way up to 4, and it includes -2, and it includes 4. So we would say, oh, y is between -2 and 4. Now that's a great way to write it, but that's not how we're going to write it anymore. We're going to use interval notation. Okay, so with interval notation, we have an equal here. So we'll put that square bracket for -2, and it goes all the way up to 4. Again, there's an equal here, so we put a square bracket. And there aren't two separate ones. I don't need any unions or anything on this one. So this would be the domain in interval notation, and this would be the range in interval notation. Okay. All right, let's look at these other ones and see if we can get through these ones. All right, so the domain, okay, for this one, well, the domain, okay, the smallest possible value is 3, and it includes that. So I would put, or sorry, I didn't say -3. Okay, -3, and it includes that. Put a square bracket, and then the largest value of x is, well, up to 2, but doesn't include 2. Okay, so it goes up to 2. It doesn't include 2 though, so I put a parenthesis there, a round bracket, a parenthesis, to show that it doesn't include 2. And then the range, okay, those are the y values. The smallest y can ever be, and this one, I guess, is -5. That's a closed circle. And then it can be any value up to 4. And that's also included. Okay, now this one is going to be a little bit tricky. Okay, so the domain on this one, okay, so this goes off forever. You can, there's little, this is a hyperbola. Okay, so this keeps going on and on forever. Okay, so it goes, from on, and then when it gets to 2, there's an asymptote there. It will never be 2. Okay, but then on the other side of 2, I mean, it's approaching this, and it goes off to infinity. So this part of the domain would be -infinity. Now you always, always, always put a parenthesis with an infinity, because there is no such number as infinity. Okay, you can't put a square bracket there and say, oh, -infinity is part of this loop. It's not a number. Okay, so you have to just put a parenthesis there. All right, and then it goes all the way up until it reaches 2, but it doesn't include 2. So 2 will also have a parenthesis. Okay, and then the rest of the domain will be starting at 2, but not including 2, and then it goes on and on and on and on forever. Okay, so it goes to positive infinity, but of course it can't include that because that's not a number. Okay, and then the range is somewhat similar. So the range is all the y values. Well, from -infinity, it'll go up this way, and then there's a horizontal asymptote on the x-axis, so where y is equal to 0. So it's going to go from -infinity up to 0, but it won't include 0 because that's an asymptote. And then on the other side of 0, it'll continue going up, 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 up forever, all the way to positive infinity. Okay, so that's how you would write the domain and range in interval notation. Okay. So let's say we have a few different functions and we want to find the domains of them. So there's some restrictions on certain kinds of functions, so let's review that. So if I want to find the domain of this function, well, I know that for real valued functions, I can only take the square root of non-negative values. Okay, because I'm not talking about complex numbers, I'm talking about real valued functions. So that means whatever's under the square root has to be, non-negative. So x plus 2 has to be greater than or equal to 0, which means that x has to be greater than or equal to negative 2. Okay, so if we want to write this in interval notation, okay, there's an equal to 2, so we can put, this is our domain, we can put negative 2, and then x will be values that are greater than that, so it's going to keep getting bigger and bigger and bigger and bigger, and there's never going to stop. It goes all the way to infinity. Okay, so there's the domain for that function. Okay, let's try this one. Okay, here, just like the previous example, we know that whatever's under the square root has to be non-negative. So 6 minus x has to be greater than or equal to 0. Okay, if we add x to both sides, okay, or you might want to rewrite that as x less than or equal to 6, just so you can see that nicely. Okay, so we've got that. We've also got this denominator, and the denominator can't be 0. Okay, so the other thing we have is that x can't be 0. Okay, so we have all these values that are less than 6, but except we have to skip over 0. So sometimes it's easier if you maybe look at this on a number line and think about, here's negative infinity, and it's going to go up, okay, and here's 0, and we can't have that, okay, and then we're going to jump, but anything up until 6, okay, we can have that. So all of this stuff. So you don't have to draw this out, but this will help you, okay, at least have that in your brain. So if I'm going to write this in interval notation, I've got to go from negative infinity, okay, up to 0, but I can't include 0. And I have to put that together with 0 all the way up to 6. And I will include 6. So that will be my domain. Okay, let's look at this one. All right, for this one, if we want to look at this, we should probably factor it first. So this is x plus 2 times x minus 2. And this one is x's and x's. And let's see, negative 3 and negative 2. Okay, so there's no restrictions in the numerator. The numerator can be anything we want. It's the denominator that has issues, right? The denominator can't be 0. How could this product be 0? Well, if either of these factors are 0. So here we know that x can't be 3, because that would cause this factor to be 0. And we know that x can't be 2, because that would cause this factor to be 0. Okay, so once again, it might be helpful to think about, like, here's a 2 and here's a 3. Okay, and all of this stuff and all of this stuff and all of this stuff is included, but not 2 and not 3. So if we want to write this in interval notation, okay, so we've got negative infinity all the way up to 2, but it can't include 2, and then put that together with all the numbers from 2 to 3, can't include 2, can't include 3, and then put that together with 3, and then go on forever towards infinity. So that would be our domain. Okay. Another function that has restrictions on the domain are log functions, natural log, any log, common log, whatever. Okay, so remember that you can only take the log of a value that is greater than 0. Okay, so this value has to be positive. So that means that x squared minus 9 has to be greater than 0, which means x squared has to be greater than 9. Okay, so if x squared is greater than 9, let's think about what that means. Well, that means x could be greater than 3, but that's not the only thing. X could also be less than negative 3. Right? Because if I do negative 4, but I square negative 4, I'll get 16. Okay, and 16 minus 9 is a positive number. Okay, so these are my two things. So if I were to draw this out, okay, here's negative 3, and here's positive 3. Okay, so all of this stuff here will work, and all of this stuff down here will work as well. Alright, so the domain of this one would go from negative infinity up to negative 3. Okay, none of this stuff in the middle, because that will cause negative values, and we can't have that for a log. Okay, but once we get 3 and bigger, we're fine. Okay, so once again, there's open circles, there's no equals, so we have to put parentheses there. Okay. Okay. And we already talked a little bit about the vertical line test, but here it's written out. It's in its definition. So a curve in the xy plane is the graph of a function. Oh, this is supposed to say of x if and only if no vertical line intersects the curve more than once. Okay, so let's look at a few different examples and we'll decide if they're functions based on whether they pass the vertical line test. Okay, so this one over here, okay, there is this spot right here, but notice, okay, this one is open, this one is closed, so a vertical line is only going to contain this point. It doesn't contain 2. So this passes the vertical line test. So it is a function. Okay, how about this one? Is hyperbola. Okay, well, hopefully you can see pretty clearly, you know, if I draw this vertical line right here, it intersects twice. This fails. So this is not a function. Okay, how about this parabola? Well, a parabola, no matter where you put your vertical line, it only passes through once. So this passes. So this is a function. Okay, and this one is a little bit more complicated. This is like something that we graphed towards the end of pre-calc. Okay, so everything only passes once. So there's an asymptote here, but remember this approaches the asymptote, and it'll never be vertical. It's getting closer and closer and closer and closer, but it never is actually 2 points on top of each other. Okay, same with this part that's approaching the asymptote. It never actually goes vertical. It's approaching this, getting closer and closer and closer, and there's never 2 points right on top of each other. Okay, so no matter where I look here, okay, this one also passes the vertical line test, so this one is a function. So I know those asymptotes are tricky because you start looking at this, and because it's getting so close and you can't see the fine detail, you're like, I don't know, is that might be vertical, but it's not. So if you see that there's an asymptote there, it's definitely not vertical. Okay. The next thing we want to look at is what piecewise functions are. So piecewise functions are functions where the rule changes for different intervals. So for instance here, the piecewise function is written out. For all x values less than or equal to -2, the way we define the function is the rule negative x minus 7. But between 2 and negative 2 and positive 2, it looks like x squared, and then after 2, the value is always 6. Okay, so if we were going to graph this, we've got to do these in these little pieces here. So let's look at from -2, so here's -2. So basically just ignore the rest of it, but from that it's going to look like negative x minus 7. Okay, so negative minus 7 would be down here, Let me see, let me grab a. Okay, so that's not part of it, but I just want to put my there. And then it's got a slope of -1, so it should rise 1, 1, 1, rise 1, 1, 1. Okay, I think it should go through like that. But it only goes to -2. Okay, so it'll include this point right here. And it'll have all of this. Okay, so for everything less than and up to -2, it's going to be points that would fall on that line. Okay, now once we get up to -2, all the way up to +2, so that's between here. Okay, it's going to look like the parabola x squared. Okay, well that would be a parabola where it's got a vertex there, and then it goes here, and then at -2 it would be up at 4. Now there's no equal there, okay, and so I'm going to have to put an open circle here at 4, okay, and show that it goes, it's a parabola that looks like, you know, a normal parabola, but it stops right before it gets to 4, okay, or where the x value is -2, because the x value for -2 is defined down here. Okay, now this one on the right side, it goes all the way up to 4, okay, because that one at 2, that's included. Okay, and then when x is greater than 2, so any little bit tiny after 2, the value is 6. So it won't be at 2, but anything up to 2 is 6. So if it's 3, it's 6. If it's 4, it's 6. If it's 4.7, if it's 5.832, okay, so all those values. So that would be the graph of that piecewise function. Okay, now let's say we had to write the graph of the piecewise function for this one. Okay, so we can see these 3 different pieces pretty well. So if we wanted to define this, okay, well our first interval would be all values that are less than or equal to 1. So this would be for x less than or equal to 1. So when it's less than or equal to 1, it looks like a parabola with vertex at 0, 0, or just normal parabola, so x squared, parent parabola. Okay, and then when now we don't want to include 1 here because that's open, so it has to be strictly bigger than 1, and then it goes all the way up to until 2, but it includes 2 because there's a closed circle there. Okay, so for any of those values in that range, it's always 3. And then finally this part, if it's bigger than 2, it can't include 2, but when it's bigger than 2, it looks like this line. Okay, so that line, if you follow it back, would have a y-intercept of 0 and a slope of 1. That's just the line y equals x. Okay. Alright, so that's piecewise functions. Now, a special case of piecewise functions are these things called step functions. Now, the most common step functions that we've probably seen in our past are the greatest integer function, also sometimes called the floor function. I think it's easier to understand when I to call it the floor function. So, if you can see this, this is, okay, so the floor function. So that says, so whatever input I have, I take an integer, that the greatest integer that I can find that's smaller or equal to x. Okay, so if you think about, you know, here's 2, here's 3, what about for 2.4? So for 2.4, okay, if I follow that up, that evaluates to 2. So 2 is the biggest integer that's less than or equal to 2.4. It's also the biggest integer that's less than or equal to 2.3 and 2.1 and 2.01 and 2.0000493, right? So all the way down to, and even 2. 2 is the biggest or the greatest integer that's less than or equal to 2. Okay. And this is called a step function, and you can see why, because it just looks like these little stair steps that go up. Okay, the least integer function is also sometimes called the ceiling function, and that's written this way. Okay, so this is the least integer. Okay, that's the smallest integer that is greater than or equal to x. Okay, so once again, like here's 2. If I do 2.4, okay, that evaluates to 3. That's the smallest integer that's larger than or equal to 2. Okay, same thing for 2.3 and 2.1 and 2.4, 2.07, but when I get to 2, well, now for 2 is the greatest, or the least integer that is greater than or equal to 2, because it's equal to 2. Okay, so these are very similar, but notice like the open circles are on the other side. So they're just slight variations. Now those aren't the only step functions. Those are just the most common ones that you've seen, but maybe we have something like this where we have a cost of printing t-shirts, and if you're gonna buy 20 or less, every t-shirt costs $20 a piece. Okay, but if you buy them in large quantities where you get more than 20 shirts, well, the price goes down. Okay, so if you buy anything from 21 all the way up to 40 shirts, okay, then you only have to pay $15 per shirt. If you have even more, between 41 shirts and 80 shirts, then you only have to pay $10 a shirt. And if you have more than 80 shirts, you only have to pay $5 a shirt. So something like that. So notice it's not quite even intervals like these ones did, where everything's exactly the same length. Okay, so this one's longer and this one's infinitely long, but that's fine. Okay, I would have probably also said this should have been a discrete function. I probably would have had little dots on here. I can't buy 21.73 shirts, so I maybe would have had little dots all along here, but okay. And then here's the cost of postage. This one is not discrete. It makes more sense. So if you have anything that weighs up to an ounce, okay, it costs 39 cents to mail it. Or if anything over 1 ounce up to 2 ounces costs 41 cents. Anything over 2 ounces up to 3 ounces costs 43 cents, and so on and so forth. Okay, so those are all examples of step functions. All right, our next concept is symmetry. Okay, so if a function f satisfies this, f of negative x equals f of x for every single x in the domain, then it's called an even function. So here's some examples. So if I think about, here's x, and if I go out to negative x, okay, now if I look at the value here, this is f of x, and if I look at the value here, this is f of negative x, okay, those are exactly the same. And that's true for each one of these graphs. Sorry, I don't know what happened when I printed these. Okay, so if here is x, here's f of x. So if I go the same distance in the other direction, if this is negative x, this is f of negative x, and once again, these are exactly the same value. Okay. Cosine is a classic example. So let's say, I have the cosine of, 60 degrees, and I go out to negative 60. Those two values are going to be exactly the same, right? Okay. So, this is the definition, but visually by inspection, if you can see the graph, you'll know that it's even if it's symmetric about the y-axis. Okay, so even functions are symmetric about the y-axis. Okay, and then odd functions. Okay, so again, with odd functions, we know something about f of negative x, but this time it's slightly different. So if a function satisfies that f of negative x equals negative f of x, okay, all the time for every value of x in the domain, then it's called an odd function. So here's what we have. So if I go out to x, okay, here's f of x, and if I go out to negative x, okay, so this distance right here and this distance right here are exactly the same. So in terms of absolute value, this value and this distance are exactly the same. But this one is in the negative direction. This is negative f of x. Okay. So those two distances are exactly the same. True here again. So if I go out to x, okay, there's f of x. And if I go out to negative x, okay, f of negative x, if I look at that, it's going to be negative f of x. It's exactly that same distance. And then our sine function is a classic example. So this is like a x cubed, that's another classic example, but we've also got the sine of x. So if you go out to, you know, sine of 60 and sine of negative 60, okay, you're going to have a positive value here and a negative value here, but the absolute values are exactly the same. Okay, so this one obviously is not symmetric about the y-axis. It's also not symmetric about the x-axis, but it is symmetric about the origin. So odd functions, okay, are symmetric about the origin. And basically what that means is you can take, okay, the one part of it and you can do a 180-degree rotation and it'll land on the other part. So take this one, do a 180-degree rotation, it lands right on top. Take this, do a 180-degree rotation, it lands right on top. So that might be an easier way for you to see that it's symmetric about the origin, as you get that 180-degree rotation around the origin. Okay. So let's look at a few examples of these, and we want to look at these and decide if these are even functions, odd functions, or neither. So we're going to go to our definition. Okay, so remember, even functions will have to satisfy this. Okay, odd functions have to satisfy this. In either case, we want to look at f of negative x and see how that compares to the original function f of x. Okay, so for each one of these, we just want to look at what f of negative x is and how that compares to the original function. So, again, think of this as f of box equals 4 box squared minus 7. So I would take 4, I would put minus x in the box and square that. Okay, well when I square a negative number, I just get a positive, so that would be 4x squared minus 7. Okay, so what we see here is these are exactly the same. So f of x equals f of negative x, so it's even. Okay, let's try this one. Okay, once again, we just need to look at f of negative x. So I'll put negative x in the box, put that to the 5th power, minus 2, and put negative x in the box. Okay. And so if I take a negative number to the 5th power, that will be a negative. So that's going to be 5 times negative x to the 5th. And then negative times negative is positive 2x. Okay. Now right now it's hard to tell how it's related to this one. Okay. So there's a plus 2x here instead of a minus. Let's go ahead and factor out a negative 1. Or factor out a negative. So if I factor out a negative, I would have negative and then 5x to the 5th and then minus 2x, because negative times negative is the positive we need. Okay, so we have the only thing that's different between f of x and this is that negative sign, right? This is the same thing as f of x, so this is negative f of x. Since f of negative x equals negative f of x, this one is odd. Okay, let's try this one. Let's look at f of negative x. So once again, put in negative x and square it. Put in negative x. So I get 7x squared, and then minus 5x plus 3. Okay, well, it's definitely not equal to this one because the sign is different here. And if I factored out a negative, this one would have the same sign, but then these ones would be different. So there's nothing I can really do to this to make it equal to this or to make it the opposite of this. So this one is neither. Okay, let's try this last one. All right, so I would do 2 times negative x over negative x squared plus 10. Okay, I'm going to rewrite the denominator first. That's x squared plus 10. I've got an even power there, so that'll be positive. And then for this negative, this is going to be 2x, and I'm going to write the negative out front so it's really obvious. Okay, so this part of it is just h of x. So this is negative h of x. Since h of negative x equals negative h of x, this one is odd. Okay, and our very last definition, okay, we've got increasing and decreasing functions. So a function is called increasing on an interval I if no matter, okay, if you take a value x1 and it's smaller than x2, then the value at the function at fx1 is less than the function at x2. Okay, so let's think about what that means. So here I've got, here's negative 3 and here's negative 2. Negative 3 is less than negative 2. And then if I look, okay, here, this is f of negative 3 and this is f of negative 2. Okay, this one is larger than that one. This is not true, so it wouldn't be increasing here. It would be decreasing. And then when you look at it, that makes sense, right? Well, let's look over here where it looks like it's increasing. 0 is less than 1. I guess this, this should have been negative 2. This should be negative 2.5. Okay, so 0 is less than 1, and f of 0 is less than f of 1, and so it's increasing there. Okay, f of 0 is less than a half. It's increasing. F of 0 is less than f of 0.5. It's increasing. Okay, so you can see that it's decreasing here, and then it starts increasing, continues to increase, and then it starts decreasing again. Okay. And this one is decreasing, increasing. Here it's neither increasing nor decreasing. This is just called constant. This is not increasing or decreasing. And then we've got increasing, decreasing, increasing, and then again constant. Okay, and this one is always, always, always increasing. It's always, always getting bigger or never getting smaller. So this is increasing everywhere. All right, so that does it for section 1.1. And your very quick review of everything you ever learned about functions.